We've gotten quite a few questions from section 9.7, so let's take a look at them. First question we had was 2D, which I think is a really good example question. It's a 30, 60, 90 triangle. I think I probably should have labeled those. It's a little 30, 60, 90 triangle. So when I do these, I always turn them the same way. And you may not need to do that, but I'm just a very visual person and I have to see what the pattern looks like. So remember, for a 30, 60, 90 triangle, it is half of an equilateral triangle, okay? And so you've always got that side length here that's x, that's your short leg. Remember, the short leg's always across from the 30-degree angle, so if the picture's not drawn to scale, that's something you really need to make sure you're looking for. So this is half of an equilateral triangle, so we know that this whole side here would be 2x, and that means, of course, that this whole side over here would be 2x. And if you went through the Pythagorean theorem here with these values, you'd find out that the third side was x radical 3, okay? So we have a lot of 3's occurring in 30, 60, 90 triangle problems. We've got 3 different angle measures, we've got 3 different side lengths, we have a radical 3 showing up on one of the sides. Okay, so remember, the pattern here is you double the short side to get the long leg, you multiply the short leg by radical 3 to get the long leg, okay? So remember, when you're going from the short leg to longer legs, you're multiplying. When you're working backwards, you're going from a long leg back to that short leg, or a hypotenuse back to that short leg, you'd be dividing. Okay, so if you take a look here, we're looking for this side here. I always try to get the short side first because that's what all the patterns are based off, is that x side, all right? So this side got multiplied by radical 3 to give you the length of 7. Okay, so I want to work backwards. I want to go from the long side back to the short side, which means I need to divide by radical 3. Okay, remember though, you do want to rationalize your denominators. You don't want to leave a radical in the denominator. So while that's a correct answer, it's not in the best form. Remember, from algebra 1, you can multiply the top and the bottom by the radical. You're really squaring the square root, right? Radical 3 squared is 3. And on the top, you get 7 radical 3. You've got a whole number and you've got a radical. Check. Does 3 go into 7? No. Is there greatest common factor that I can divide out of 3 and 7? Nope. You're just going to end up with 7 radical 3 over 3. And again, I know it's weird because you're expecting to see a radical 3 over here on this side, but because we had to divide by radical 3, it's actually showing up on that side. And again, you can check it. You've got 7 radical 3 over 3. The idea is if this gets multiplied by radical 3, we should get this. And notice, if I multiply by radical 3, I get 21 over 3, which is equal to 7, which is what that side's supposed to be there, okay? Now, the last part's easy. We double to get the side up here. So 7 radical 3 over 3 multiplied by 2. Remember, 2 is 2 over 1. So your numerator is getting multiplied there. Whole numbers get multiplied. We get 14 radical 3. And of course, the bottom there is just getting multiplied by 1. So it's 14 radical 3 over 3. Again, be careful. Some of you are going to want to try to simplify these 3's here, but that's a whole number, and a whole number can't divide into a radical. We showed that a couple days ago. So anyway, it just stays 14 radical 3 over 3, or if you want to write it as 14 thirds radical 3, you can. People don't usually use mixed numbers with radicals. So yes, this would be the same thing. What is that? 4 2/3 radical 3, but nobody does that. So leave it in this form, or 14 thirds radical 3. But that's what's going to be in the back of your book. All right, let's take a look at 9b. 9b, I believe they told you it was a kite. So of course, the big fact from kites that we remember from chapter 5 is the diagonals are perpendicular. One diagonal is being bisected, okay? They told us that TW has a length of 10. So we've got a length of 5 there and a length of 5 there. Notice they didn't give you angle measures, okay? We always get a couple people who decide to just start randomly deciding that every triangle is a 30, 60, 90 triangle or something like that, okay? If you don't have angle measures, if you don't have something that would lead you to angle measures, like knowing you have an equilateral triangle, you're just going to have to use the Pythagorean theorem or look for Pythagorean triples or something like that, okay? So this has nothing to do with 30, 60, 90 triangles. Okay, if we start looking at things here, we want the length of WX, for example. This is a little 5, 12, 13 triangle. So again, knowing your triples can save you a lot of time. Again, if you don't know your triples for some reason at this point, which should have been drilled into you at this point. 5 squared plus 12 squared is equal to c squared. You could solve that, but learn your triples, okay? You should be able to do that in your head. By the way, this triangle here, you know, you've got, we're looking for the length of TR, which is this one down here. So notice we've got two side lengths there. Yes, you can do the Pythagorean theorem, 5 squared plus 5 squared, and take the square root and get the length there. But what kind of triangle is that? It's a right triangle with two equal sides. Right, it's an isosceles right triangle. We know an isosceles right triangle, in addition to having two equal sides, would have two equal angles. And we've got 90 degrees left because we already used up 90 degrees there. So this is a case where we can find out. That's a 45, 45, 90 triangle. And of course, we know the sides get multiplied by radical 2 to be the hypotenuse there. So again, this section, these are fast, okay? If you know your triples, if you know your 30, 60, 90, and 45, 45, 90 patterns, most of the problems in this section should be able to be done mentally. Okay. Over here, same kind of thing. We've got a 60-degree angle and a 30. The angles of a triangle add up to 180 degrees. So we've used up 90. That's going to force that angle measured there to be 90. So make sure you're always filling in what you don't know or what you're not given. So we got a big 30, 60, 90 triangle right here. And actually, that means we can already start filling in, since the big triangle's at 30, 60, 90. Going back to the pattern, this is the short side, right? It's opposite the 30-degree angle. So we can double the short side to find the length of the hypotenuse. That's going to be 12. We can multiply it by radical 3 to give us a 6 radical 3 over on that side. And we're just about done here, actually. So on this triangle here, we need these two segments. This is a little 30, 60, 90 triangle. And you know, you might want to turn it a different way with the hypotenuse here. Remember that the hypotenuse is double the length of the short side. So to get back to the short side, you can divide the hypotenuse by 2, you get 3. You multiply it by radical 3 to get the length of the long leg. So we're going to have a 3 here. We're going to have a 3 radical 3 there. Okay. And anyway, at this point, this is a 30, 60, 90 triangle, okay? This is the short side. It's opposite the 30-degree angle, okay? So the pattern says multiply it by radical 3. So we're going to take 3 radical 3, and we're going to multiply it by radical 3. You need to simplify that. Radical 3 times radical 3 is radical 9, which is 3. 3 times 3, of course, is 9. And by the way, you already knew this was 12, and you knew this was 3, so you could have found that without using the 30, 60, 90 patterns. Okay, we want the ratio between the perimeters. So the perimeter of VSR is 9 plus 3 radical 3, and those are not like terms, so that's our first ratio. And then VRT's perimeter, VRT is the big triangle, okay? Its perimeter is going to be 6 plus 12 is 18, plus 6 radical 3, okay? And going back to 3rd grade, anytime you've had a fraction, anytime you've had a ratio, you always look for greatest common factors that can be divided out. So 3 divides out of these terms here. 3 also divides out of those 2 terms there. So I would probably write the final ratio as 3 plus radical 3, if I divide both of these by 3, to 6 plus 2 radical 3. And that's probably going to be, 3 plus radical 3. Ooh, this is interesting. This probably goes to kind of high end if you think back to your Algebra 1 experience. I'm not sure if a lot of you have seen this. You can actually factor a 2 out of both of these. If you factor a 2 out of both of those, you actually get 3 plus radical 3 to 3 plus radical 3. If you notice, this is just double that. So this is actually going to simplify down to a 1 to 2 ratio, which kind of surprises me. So anyway, on a low level, I'm guessing most of you had 9 plus 3 radical 3 to 18 plus 6 radical 3. Again, it looks like we can break that down. Let me check and see if that's right. 17b. Yeah, it does simplify down to 1 to 2, so that's kind of interesting, and that's tough to see. And after you've had Algebra 2 and you're really used to factoring, those of you who are doubling up probably saw that already, but If you're not doubling up, you might not have seen that one. So actually just a 1-to-2 ratio, 17D. Good question there, and I'm guessing that's why a lot of people were asking that. Okay, 24. Of course, coming out of section 8.5, we've had drilled into us that idea of the angle bisector theorem, and we know that the ratio between these parts is the same as the ratio between these parts, with that bisector dividing up the triangle proportionally. This actually doesn't end up being an angle bisector problem. So for those of you who are kind of spinning your wheels trying to do something with that, that won't incorporate the angle measures. Here's the deal. You've got a 90-degree angle, which means you've got, these problems are all about angle measure, if you haven't picked up on that. So we've got a 30 over here, we've got a 90. You've got 60 left for this angle, which means this big triangle here, which is drawn a little bit more to scale in the book, is a 30, 60, 90 triangle. That also means that this is a 30 and that this is a 30 over here. And if you look at this triangle here, so again, I cannot urge enough, make sure you're filling in your angle measures, because again, this section and most of the future sections working the triangles are going to come back to something having to do with angle measure. Anyway, now you notice this is an isosceles triangle. Okay, again, not drawn to scale in my picture, but I think the book does it justice a little bit more. So our two base angles are 30. We know the sides opposite those base angles are going to be congruent. So we've got a 3 here. This whole side here is also going to be 3. Okay, now this is a little 30, 60, 90 triangle as well. Okay, so this is the hypotenuse. Okay, remember the hypotenuse is always double the short leg. A short leg is the one opposite the 30-degree angle here. So take half of that, that's going to be 3 halves, or 1.5 if you really have to use a decimal. And then remember that the short leg gets multiplied by radical 3 to be this other side. So y is going to end up being 3 halves times radical 3. Radical 3 is radical 3 over 1. So I think in the back of your book they're going to write that as 3 radical 3 over 2. Technically the same thing as 1.5 radical 3. It's not wrong, it just fraction's a little better answer. And then the last thing here, you're looking at this triangle here. Tell you what, let me draw this separately. I'm just going to draw the isosceles triangle. It's a little misleading here. The isosceles triangle there at the bottom, we know this is 3, we know this is 3, we know that's a 30, we know this is a 30, okay? One of the really important strategies, and we've seen it in previous sections, is creating right triangles. Altitudes of triangles, altitudes of trapezoids, altitudes of different shapes. Break shapes up into right triangles. Check this out. You see 30s, okay? If you see 30s there, that's a sign, probably some 30, 60, 90 triangles can be made here. Drop in that perpendicular, okay? 30 and 30 adds up to 60. That means this whole angle here was 120, which means that's a 60 and that's a 60, okay? These are little 30, 60, 90 triangles as well. And so anyway, to close this one out, we're trying to find the length of this whole side. That's the hypotenuse. We know that half of that's going to be 3 radical 2. This is the long leg, so it's going to be 3 halves times radical 3, or 3 radical 3 over 2. And then it's the same triangle over here, so you're going to have a 3 halves radical 3 here. That's a 1.5 radical 3 plus a 1.5 radical 3, just ends up giving you 3 radical 3 as your final answer for that side. Let me check that, make sure that's right. That is absolutely correct. All right, so some really good strategies here. I think these were great questions. Again, cannot stress enough. Look for angle measures. If you see a 30, or if you see a 60, or if you see maybe 120 that can be divided by 2 to give you a 60, be on the lookout for cases where you can get some 30, 60, 90 triangles, okay? Doesn't replace everything that we've done previously, but when you have information about angle measures, it's going to make a big difference.